So let's talk about linear functions. We are now in chapter 3. So linear functions, no surprise, are about lines. And as we get into this, I want to look at some general patterns for kinds of curves that we'll see in this class. As you see here are 6 of them. We've already kind of run through some basic characteristics of these in terms of concavity. Notice that patterns 3 through 6 all have some kind of curving going on. They have concavity, but patterns 1 and 2, being linear, do not. They do not have concavity. So linear functions are concerned with patterns 1 and 2. And if we talk about these patterns in terms of rate, patterns 1 and 2 are the ones that have constant rate. Okay, so remember that. Linear is constant rate. Okay? Increasing or decreasing at a constant rate. Okay. So with that in mind, let's look at the most basic form of a linear function. And here it is. A linear function can be written in what's called slope-intercept form, which is the following. F of x equals ax plus b, where a is the slope of the line, and that's this term right here. You will very often see this written as m. Our textbook uses a, but m is also very commonly used. And the b term has a couple of names. It's the vertical intercept. It's also called the y-intercept, and it is the value of the function when x equals 0. Okay, so if I put in f of 0 here, I get whatever a is, it's a times 0 plus b, and a times 0 is just 0, and so that is just b. Hence, f of 0 equals b. Okay, so that's why we call this the slope-intercept form of the line, because the two things that comprise it are the slope and the y-intercept. Okay. All right. Now I know I haven't really defined slope a whole lot in a whole lot of detail. We have talked about it some, but we're going to talk more about that. Okay. Let's talk about some other general characteristics of the linear function. Number 1, its domain. The nice thing about linear functions is, just as math functions, if we're not talking about an application, then the domain is always going to be all real numbers, and that's pretty easy to remember. However, like I said, don't forget a model domain, which is something that we very commonly have in this class. It will very often restrict our domain. So in fact, even though it's a linear function, a lot of times when we actually get into working with it, the domain will not be all real numbers. It'll be some subset of that. Okay, and that pretty much goes for the range as well. The range is also all real numbers. Now there is one important caveat to that, and that's right here. If a is not, as long as a is not equal to 0. So as long as the slope is not equal to 0. So what is that talking about? Well, if a equals 0, that's basically saying that we have a horizontal line. And a horizontal line like this, what is its range? Its range is definitely not all real numbers because it doesn't go up or down. It stays at the same level height. So its range is actually just whatever this particular value is, which is b. So the range for a horizontal line has, let's just write it right here, has range a single value, b. So that's a notable exception. Okay. Some other general characteristics of the slope are given in these last two bullet points. If we have a positive slope, then the line increases at a constant rate. If we have a negative slope, then the line decreases at a constant rate. So positive slope means the line goes up. That's a greater than 0. And negative slope, line goes down, a less than 0. And then the other scenario is 0 slope. Then the line is horizontal. Okay. Okay, with that in mind, let's now look at an example of math modeling using a linear function. This is a population model for Portland, Oregon. Now this model is given in thousands, so be aware of that. So when you see like 1.3, that's 1.3 thousand. Or 1,300, I guess. Between the years 1980 and 2010 can be modeled by the function population time t equals 7.460 plus 367.1, where t is the number of years after July 1st, 1980. So this is elapsed time. This is an elapsed time model. The clock has been reset. Time starts at 0. But 0 time represents July 1, 1980. Okay. So, according to the model, what was Portland's population in July 1st, 1980? Well, that's times 0. Okay. Times 0. So we're just trying to find P of 0. Now, you plug 0 into this equation up here, and this term will be multiplied by 0 and therefore will disappear, will be 0, and so we're just going to be left with that value, 367.1. Now keep in mind that's 367.1 thousand, so that's 367,100 people. Okay. All right. Predict population, Portland's population on July 1st, 2010. Well, 2010 is 30 years after 1980. So this is P of 30. That's an input. Looking for an output. So you can either just calculate this directly or you can use vars y vars. Don't forget, if you're going to use this method, you actually have to type in the function as y1. So we have to enter this function is y1. Okay. All right, and we'll do that in just a second. Actually, why don't we just go ahead and do it now? So let's type in our model. That's from a previous problem. So y1 is 7.46x plus 367.1. Okay. I want to know the value of the function at time 30. 30. That's 30 years. Now notice I didn't put in 2010, I put in 30. Okay. And that's 590.9. So that's 590,900 people. Okay. What about the range? We're given here that the domain is 0 to 30. I hope you understand where that's coming from. That's based on the fact that our model goes between 1980 and 2010. In elapsed time, that's 0 to 30. So what would its range be? Well, we can use a little trick here. I know this model. Actually, let's do this. Let me just graph this since I have my calculator. Sorry. Let me change my window to be 0 to 30. And then we'll do zoom fit. So you can see that the model is sloping upwards. It has positive slope and it's moving up, increasing at a constant rate. That rate of increase, by the way, is 7.46 thousand people per year. That's just the slope of the function. Right, so to find the range, since this is just going up and it's not kind of curving up and then down, and we don't have any like intermediate high points that might throw this off, I can find the range in a very easy way, which is that I can just evaluate the model at its endpoints, and that'll tell me the low and high parts of the range. So what I'm saying is I can just evaluate p of 0 and I can evaluate p of 30, and those two numbers will give me my range. Now I actually already did that, right, in the previous two parts of the problem. So we actually have the range already, we just kind of have to make it official. So our range will be 367.1, and let me bring up my calculator. I did this just a moment ago and that was 590.9. Okay. Now let me caution you, you can't always find the range in this method. For example, imagine this. Imagine the function did that, okay? And I wanted to find the range from here to here, okay? So if that was my domain, and the range is going to be from this point up, right? But if I just found the value of the function at this point and the value of the function at this point, they would both be, well, this would be 0 and this would be like right here. So it wouldn't tell me, I would never see this high stuff up in the middle. And the reason that, why do we have this problem? Well, because we have all this curvature. With a linear function, that doesn't happen. It just goes straight up. So I can easily find the range by looking at this end and this end. Or even if it goes down, I can find the range by looking at the values of the function at each end. That's a nice little trick. Okay, one last part. According to the model, in which year did Portland's population reach 500,000? Okay, this is a type 2 question. That's an output. So, how do we do that? Calc intersect. Okay, so let's do it. We go to y equals, we type in 500 as our second function. That's our horizontal function. Now we've got to figure out the appropriate window. So we know it's 0 to 30. Actually, since we know that this window is 0 to 30, we've already graphed this as our domain. We will probably be okay just graphing this directly. And we are, so we don't have to worry about the table in this particular example. In some situations, though, you do actually need to look at the table to figure out where to see the intersection, but in this case, we didn't have to. All right, so now to find the intersection, we go to second trace, which is calc. Number 5 is intersect. First curve, second curve, and scroll over to your guess, which looks to be there. Hit enter one last time, and we have this as our value. 17.815, so 17.815 years after July 1st, 1980. Okay, now notice that corresponds to July 1st. Whenever we have a population model based on U.S. Census data, we're going to assume this. We're going to measure time from the middle of the year, okay? Now, I just did all these computations, and there you see the answer. Okay, and finally, here's our answers listed in a slightly more legible format. All right, we'll pause the video and come back and do some more stuff with this. Oh, I guess the last thing I should say is the year, actually. Pay attention to this. Since we're in July 1st, 1980, that's 0.82 years after the middle of 1997, and so that puts us in 1998.